let's take a look at page 275 in your workbook, and we're looking at solving more complex radical equations. So we've got a couple of examples to work through. In the first case, we've got Billy, who's been given this radical equation, and you can see that there are two radicals there, and both of them have binomial radicands, which makes things a little bit more complex than the previous examples we've looked at. So let's take a look at what Billy's done first. And so he's rewritten the question right here, and then following the step that we had suggested, which was pick the radical that is a little bit more complex, which is probably the square root of 3 plus 4, and isolate that one. And so he does so by adding the square root of a plus 1 to both sides. So far we are good. And then he decides to square both sides in order to get rid of that first radical. So he squares the left side, and the square root and the squared counter each other, and so we've just got 3a plus 4. So on the right side, however, we have an issue because we have 3 plus root of a plus 1 all squared, and what has Billy done is he's taken something that appears like a plus b squared, and he's decided that, and we're going to write not equals because it's not true, he squared the first term, squared 3 to get 9, and then he squared the second term, b, to get a plus 1, which is incorrect. What we have to remember is that when we're squaring that side, when we have a plus b all squared, that's the same as a plus b times a plus b. So that means that we need to FOIL, so expand a squared plus 2ab plus b squared. So Billy is missing that middle term, and that's why that's not going to work. And I'm sure he would have noticed that once he did his verification for his left side and right side. So Billy assumed that a plus b squared was equal to a squared plus b squared, which is incorrect. So a plus b all squared should equal a squared plus 2ab plus b squared. So this line is correct, and our issue is right here, and that is Billy's mistake. So let's take a look then, and we will start, why don't we start from where he was in fact correct. So 3a plus 4 is equal to 3 plus the root of a plus 1, and we are going to square both sides. So on the left side, we know that we just have 3a plus 4. On the right side, let's go ahead and expand that. So perhaps that will make that a little bit more clearer for ourselves to show that we need to, in fact, use FOIL to expand. So on our right side, then we have first, so 3 times 3 is 9, and then we have 3 times root of a plus 1, and we've got that again for our inside, so 3 times the root of a plus 1, and then lastly, root of a plus 1 times root of a plus 1 is a plus 1. So we'll clean that up. Then we've got 3a plus 4 is equal to 9 plus 1. So we've got 10 plus 6 root of a plus 1 plus a. And again, because we still have a radical, then we want to isolate that radical. So we will subtract 10 from both sides. And we will also subtract a from both sides. So we've got 2a minus 6 is equal to 6 times root of a plus 1. So at this point, we have a couple of options. We could go ahead and square both sides right away, or we can see that there is a common factor of 2 on both sides, so we could divide both sides by 2. So we then have a minus 3 is equal to 3 root a plus 1. And now, since our numbers are a little bit smaller, we can go ahead and square both sides. So on the left side, again, we need to expand and do FOIL. So we'll end up with a squared minus 6a plus 9. On the right side, 3 root a plus 1 times 3 root a plus 1 is going to be 9 times a plus 1. So a squared minus 6a plus 9 is equal to 9a plus 9. And again, we have a quadratic, so we'll set it to 0. So we'll subtract 9a and subtract 9. So then a squared minus 15a is equal to 0. And we can then factor. Got a common factor of a, so it's a times a minus 15 equals 0. So our zero product law means that either a equals 0 or a minus 15 equals 0. So a is equal to 15. So if we do our verification, we can see what happens. So let's take a look. So let's us verify first. And so we need to go back to the original equation itself. So root of 3a plus 4. So left side is root of 3a plus 4 minus root of a plus 1. And the right side was equal to 3. So let's take a look. So we're going to check a equals 0. So that means that I would have square root of 4 minus the square root of 1 is equal to 2 minus 1, which is 1. Left side not equal to the right side. So that means that this is an extraneous root then. Extraneous root. So we need to reject that answer. So let's try a equals 15. So left side is the square root of 3 times 15 plus 4 minus 15 plus 1. So that is 45 plus 4, 49, minus root 16. So 7 minus 4 is 3. That looks good because our right side is also 3. So left side equals the right side. So in fact, our solution is a equals 15. If we wanted to also just check our restrictions as well, we know that 3a plus 4 must be greater than or equal to 0. So 3a is greater than or equal to negative 4. A is greater than or equal to negative 4/3. And 15 definitely satisfies that. We also know that a plus 1 is greater than or equal to 0, so a is greater than equal to negative 1. And so you can see both 0 and 15, those two solutions that we found from solving, actually satisfied both of our restrictions. And it was actually the verification that was then able to catch the fact that one of those was an extraneous root. So a equals 15 is our only solution. Okay, let's take a look at class example number 2 on the next page. And this is a word problem. So let's read that carefully. When the square root of 2 less than a number is subtracted from the square root of 5 more than twice a number, the result is 3. So x is obviously going to be the number. So we've got the square root of 2 less than a number. So the square root of 2 less than a number, so x minus 2, that's going to be subtracted from, so minus that, the square root of 5 more than twice the number. So 5 more than twice the number is 2x plus 5. So the square root of 5 more than twice a number, subtract the square root of 2 less than a number. The answer is 3. And so you can notice, or you've probably heard how many times I read that aloud as I'm walking myself through that equation. Okay, so give this one a shot and hit pause and try to go through and solve that yourself. And then you can come back and compare. So again, as before, we've got two radicals, both of them unfortunately, or fortunately, we've got a good challenge. They're both binomial radicands, two-term radicands, and so we'll isolate the more confusing one, which is probably the 2x plus 5. So we'll add the root of x minus 2 onto the other side. So we've got root of 2x plus 5 is equal to 3 plus the root of x minus 2. Then we will go ahead and square both sides. And the reminder again is on the left side, we will just have 2x plus 5. On the right side, we'll need to use FOIL, expand, so 3 plus root of x minus 2. And I know several of you would be helped by writing that out so you can see that clearly. And we would have 3 times 3 is 9, and then that is plus 3 root x minus 2, and again plus 3 root x minus 2, and then root x minus 2 times root x minus 2 is going to be simply x minus 2. So we'll clean that up, and we've got 6 root x minus 2 plus x and plus 7. And once again, we will isolate that radical. So we will subtract x from both sides. We will also subtract 7 from both sides. So then we have x minus 2 is equal to 6 root x minus 2. So at this point, we will go ahead. There's no way that we can take out a common factor out of anything. So we will just go ahead and once again square both sides. And so squaring the left side, we need to, because it's a binomial squared, so we're going to FOIL, so x squared minus 4x plus 4. On our right side, we've got 6 root x minus 2 times 6 root x minus 2, so that is 36 times x minus 2. So that will need to get distributed in. So x squared minus 4x plus 4 is equal to 36x minus 72. We have a quadratic equation, so we want to set that to 0. So subtracting 36x, so x squared minus 40x, and then add 72. So plus 76 is equal to 0. And so ideally, we're going to be able to factor this, and given the nature of the question itself, we should be able to factor that, and it works out nicely to x minus 38 and x minus 2 equals 0, because negative 38 times negative 2 is positive 76, and the sum of those is negative 40. So that means that x must equal 38 or x equals 2. And so we will verify both of those to make sure that they work. So we're going to go back to our equation. So let's verify. So let's try our x equals 2 first. So the square root left side is square root of 2 times 2 plus 5 minus the square root of 2 minus 2. Okay, and right side was equal to 3. So that is the root of 4 plus 5, root 9, and minus root 0. So that's just 0. So that is 3. Left side equals right side. So x equals 2. That does in fact work. So let's verify x equals 38. So left side is the square root of 2 times 38 plus 5 minus the square root of x 36 minus 2, so 38 minus 2. And I hope you're noticing as we're going through these verifications that everything has a really nice way of working out. So this is 76 plus 5 minus 36. Notice how those are both going to be nice perfect squares. So square root 81 minus the square root of 36, or 9 minus 6 is in fact 3. Right side is 3, so left side equals right side once again. So we have two solutions. So the number is 2 or 38. Excellent. Let me know if you have questions, and please complete the assigned work.